www.nanohub.org.
You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
Donors and acceptors, and how the statistics of donors and acceptors, when you put electrons in donors and acceptors, are different from when you put an electron in a big solid, and like a silicon or a germanium, which has lots of atoms. Remember, donors and acceptors are like isolated atoms. An analogy would be, if you go to a foreign country, the people, of course, in that country has a way of doing their business and getting distributed in various ways they want to. But when you are a foreigner, like a donor or an acceptor, in that case, the rules that you follow might be slightly different. And that is the purpose of the discussion today. And in the process, we will also be trying to calculate or getting started towards calculating the electron number when a solid has a certain number of donors or acceptors. We will quickly review the law of mass action and the intrinsic concentration. This is something we have done before. We'll talk about statistics of dopant levels, both donors and acceptors, and then finally conclude. Now, this is something I have discussed before, 2 lectures before, that if you have a solid which is not doped by any foreign material, then in that case the total number of electron is a constant. And when you raise the temperature of the solid, let's say from 0 degree to some finite temperature, the electrons get redistributed. And if we discuss that some of the electrons from the valence band, in that case, goes to the conduction band. And the one that goes to the conduction band has been shown here in red, and the ones that, the holes that have been left behind are shown here in blue. Now we realized without donors and acceptors, then the blue, area under the curve for the blue must be area under the curve for the red, although the picture doesn't look like that well. Now we also discussed that N multiplied by P for any semiconductor, doped or undoped, is always equal to Ni squared in equilibrium. When you apply a bias, that rule will not be valid. It will be changing a little, but N multiplied by P, regardless of how much dopant you have put it in, is always going to be equal to Ni squared, a constant. And so in that case, what we said, that the left-hand side will become Ni squared, and because N is equal to P, and the right-hand side, the expression for Ni squared is effective density of state and the band gap on the exponential. And you remember that we calculated by solving this equation the number of electrons in an intrinsic material. Beta, remember, is 1 over kT, right? So always, as an engineer, we are not physicists, we are engineers, so it's always good to carry some numbers in our head, like Nc and Nv on the order of maybe 10 to the power 20. Remember, in a given band, the number of states is equal to the number of atoms. So per centimeter cube, 10 to the power 22, let's say. But remember, not all states are occupied. A fraction of them are occupied, let's say 1/100th of it. So that number, N sub C or N sub B on V, on the order of 10 to the power 20, you see. And the Eg is on the order of EV. That's what I have seen, many semiconductors, right? And kT on the order of maybe 25 milli-electron volts or so. So you can see that factor on the top can be e to the power minus 20. So that is what suppresses, although the Nc and Nv are big numbers, the gap, band gap, suppresses the number. And it sort of makes sense. You see, if you have to jump 1 eV up while your average energy is only 25 milli-electron volts, not too many can jump over to the conduction band. And that's why this number is small. So We talked about that number, and we also talked about how to locate the Fermi level or the intrinsic level for this case, right? By equating n equals p, and from that we calculate everything. You know, NC and NV you already know, Eg you know, beta is 1 over kT. So you know all these quantities for an intrinsic semiconductor, therefore you know the Fermi level. The intrinsic level and the Fermi level, the subscript I, is the same thing for intrinsic semiconductors. Now in doped semiconductors, of course our life isn't so easy. It's a little bit more complicated, and that's why we have to discuss. That's what we have to discuss a little bit more today. Remember, however, this is also an approximation. This formula of Ni squared when it is non-degenerate. If it is degenerate and the Fermi level is very close to the conduction band, in that case, this formula is not correct. Now, I have already mentioned that intrinsic concentration is too small, and therefore a semiconductor under normal temperature, you know, many of the common semiconductors, is essentially an insulator. The electron concentration is so small that if you apply an electric field, you will not even get a femtoampere of current in a given 1 centimeter solid. So we need something to do to increase the carrier concentration, and we said that this is done by doping the semiconductor. Okay, so this far we already know. Now, one thing I want to emphasize from the very beginning, that if I assume, for example, here the reds are donors in this picture and the dark blue is acceptors, no matter what I do, if I throw in a bunch of these things, this whole solid as a whole is charge neutral. Do you understand why? Because yes, a donor brings in an extra electron, but it also carries with it an extra proton, right? So it's charge neutral. Holes, yes, it has one less electron compared to all its friends, but it also has one less proton. So therefore, if you count all the protons in the solid, in this new material, and all the electrons in that solid, in that new material, the sum, when you calculate them all up, this is 0 over the volume. But in addition, if the material is homogeneous, that is, that you take the solid and put the dopants uniformly everywhere, not one more in one, a little bit more in one corner, a little bit less in another corner, not that, uniformly everywhere. In that case, you can make further this additional statement, that not only it is the integrated thing is charge neutral, but if you took a microscope and sort of a very small region, a micron cubed region in throughout the volume, you'd still find it is charge neutral within this. Only if it is spatially homogeneous, right? Because of course otherwise at every point the dopant density could be different, and so that wouldn't be correct in general. Locally, however, spatially homogeneous, this would be correct. Now I have written here P is number of holes, N is number of electrons, and this is charge. So P has a plus sign and N has a minus sign. I have also put a Nd plus. Nd plus means the donors which has given away its electron. If it hasn't given away its electron, then it's charge neutral. It wouldn't come in this equation. Only the fraction that has sort of donated its electron, those will become charged, and only the charged one will get into this equation. And similarly, Na minus is the holes that have been filled by electrons, because otherwise it's charge neutral. When it catches a hole and fills up the hole, catches an electron and fills up the hole, then it becomes Na minus, and the sum total 0. Now actually with this statement, even in a doped semiconductor, I already know what the Fermi level is. Let's see a little bit carefully that the value for the holes P is given by NV, an exponential of EF minus EV over KT. You know that, right? Because it depends on how many holes you have depends on where the Fermi level is. If it's closer to the valence band, then you have more. If it's farther away, you have less. So that's the expression for holes. The next one is an expression for electrons. You can see that there is a ECE and N sub C sitting there. Well, that's fine. Now there is an expression for Nd plus, which is looking a little strange, but it's almost looking like a Fermi-Dirac statistics. You see, I have Nd divided by 1 plus that exponential thing, and I have a little 2 sitting there, almost like a Fermi-Dirac, but not really, because Fermi-Dirac wouldn't carry around that 2 in the denominator. Is that right? And the final one is the acceptor. You see this about again like a Fermi-Dirac, except that there is a 4 sitting there in the denominator. Apart from that, Fermi-Dirac. Okay, I'm going to derive these two relationships shown here in red and blue. That will be sort of the most of the class today. But the answer of what we are after is already here. What is the only thing unknown in this expression? Do you see? You know N sub V, N sub C, ED is a donor level. In the last class we calculated that. Do you remember? That was a hydrogen levels, hydrogen-like level, M star and other things. And we also know EA is the acceptor level, wherever that was, the whole level. So the only thing that is unknown in this expression is EF. Fermi level is the only thing unknown. And as soon as I know by solving this equation where the Fermi level is, then I will insert it in the first expression. It will give me the number of holes. Insert it in the second expression, number of electrons, and so on. So I have in fact solved my problem of calculating the Fermi level. Remember, that was the unknown thing. Calculating the Fermi level in an arbitrarily doped solid. So what I'm going to do now is spend probably next 20 minutes thinking about this donor and acceptor level and why I have to use a Fermi-like function, where for the first two I did not, right? Why do I have to do that for here also? And where is this factor of 2 and 4 coming from, right? But this is a detour. Your answer is already here, okay? So now let's talk about it. Now that will be the statistics of dopant levels. Now I have already mentioned in the last class that when you have a dopant in a solid, in a semiconductor, then if the dopant brings with it an extra electron in a donor, then and also it brings with it an extra proton, electrons goes around, and you can calculate where the level is, and we will indicate that with ET. The T subscript over there is for trap. They call it trap, but you could also call it ED if you wanted to associate it with the donor level. I mean, that's just the nomenclature compared to the before. And I have also mentioned to you that you can have 1 level, 2 levels, and levels below the mid cap. Now I will give you a homework in which instead of having 1 level, you will have, let's say, 2 levels. And then you will have to rewrite the formula in the previous slide in the presence of 2 levels. Because over there I had just 1 level at ED. You should see how to handle 2 levels and you should be in good shape. Now I want to physically tell you what does a dopant do. Yes, it gives an electron, but remember it's a foreigner. It doesn't do everything that the locals do in an exactly the same way. First of all, it doesn't want to play the standard game. Assume that I have 4 silicon atoms, let's say. Now in general, when the silicon atoms were far apart, or idealized atom, let's say, far apart, then let's say each one of them have the 2 levels. This is what I meant about, last time we talked about potluck, that let's say each one has 2 dishes. And you have those 2 levels, and when you come to potluck, come close together, you share. Now remember, in each one of the levels, the size square, integrated size square within each rectangle, that is of course 1. So the electron is sitting in the own atom. when they are far apart. Now, when they are close together, what happens? That they begin to share, because the electron in the first one now can go to the second one, third one, and fourth one. So it's spending sort of 1/4 of the time in each one, its own one, and so this whole thing is spread out. But you can see still on the bottom you have 4 electrons. It is just these are spread out and they have more places to sit. This is where the band came from, right? The bottom one, let's say, was the valence band. The top one was the conduction band. This is a sharing of the states. That is where the bands came from. And that is why when you have 4 atoms per band, you have 4 levels without spin. Now, when a donor comes in, donor is a little different, because the donor levels, it has one less proton, one more proton, one more electron. It's not, levels are exactly not in the same place. And so that is what I have shown here in green. Now, when a donor comes, then it doesn't want to donate anything. It is like one of those persons who come to the potluck but keeps his food to its own. And in that case, what will happen? That the others will share, but the donor wouldn't share on its own. Of course, if you give it a little bit of temperature, then from the green, they might jump up and join the others. But you'll have to give it a little bit of energy. It doesn't do it on its own, right? And so in general, anytime you have a donor or an acceptor, in that case, the number of continuum states that you have is 2n minus 2 here with spin, because it didn't give, the donors did not give the electrons. Now, in a big solid, remember, you have a 10 to the power 22. So 2 times 10 to the power 22 minus 2, well, you don't really care that you had a few donors here and there, didn't want to share. The number of states are so many anyway, it doesn't matter. But think about a small molecule, right, where you have only a few states. In that case, these things might become an important consideration. But the main point I wanted to make was, when you have a donor, it doesn't give its states or electrons easily unless you give it a little bit of temperature. So the green level where it is sitting compared to the bottom of the band, that is what ED is or ET is, right? That amount of energy you have to give before it goes to the conduction band. Now let's talk about what rule these electrons in that donor level should follow. Now, you have done this before, so I don't really have to work very hard on explaining it. Do you remember that the formula we used for deriving Fermi statistics using the partition function? We used 3 techniques. One of them was partition function, and in the partition function method, we had on the numerator the energy level EI and the electron level NI. Those things you have. Now think about these donor levels. Donor levels have actually always have 2 levels, right? Spin up and spin down. Why I cannot ignore spin here, I will come in a second. In a donor and an acceptor, which are localized, which doesn't share its electron with everybody, you cannot neglect spin anymore. You cannot neglect Coulomb interaction anymore, right? And I will explain why. But you can get this idea first. First, you say, if both of them are empty, no electron over there, right? If you don't have any electron over there, you have energy is 0. Well, no electron, Ni is 0. And if you insert EI equals 0 and Ni equals 0 in the equation on the top, you get the idea that it will be e to the power 0. And that's 1. And that's why in the first line I have 1 over z. Okay. What about the second one? In the second one, I have one spin one spin up. You see, U is for up spin, D is for down spin. So that's why I have U and D written there. So you have 1 on the up side and nothing on the 0 side, fine. One level, 1 electron you have EI, and then 1 electron. So I have Ni equals 1, put it in, I get that expression, and this you have seen before. In the previous expression, you have seen this before. What about the third one? Well, third one is again 1 down and nothing on the upside, same expression, no problem. But the trick is, and that's what makes it donor so different, is that when you try to put 1 and 1, both up and down so close together, remember donors, they don't give out their electrons, so close together, this time they are not sitting together at all because they have strong Coulomb interaction. They will kick the other one out. The first one will sit, and anytime the second one tries to come in, the Coulomb repulsion will push it away. So this level, if you want to put 2, will require such a high energy that that configuration is not possible. As a result, I will not have any configuration associated with 1 and 1. You see? Now, so I have 3 configuration. That's the table. The probability that the donor is empty, it has given away its electron, it has 1 more proton in the core, so it's a positive charge. This is what I have. When it's empty, it's F00 is what I'm after. I want to know when both states are empty compared to everything else. And if I insert the expressions from the top table, you immediately see where this 2 is coming from. The 2 on the right hand side shown in the red, you can see the 2 comes from because you have 2 configurations which are now possible, spin up and spin down, which was not the case before. And when the donor state is empty, you get that expression, and when the donor state is full, in that case you have 1 minus F00. You can calculate the whole thing, this is no rocket science, and you will get an expression for half, an expression containing half in the numerator on the right hand side. So good. So this is it's not really Fermi-Dirac statistics, right? If you derived it, it would have carried your name. So in that case, it's a slightly different than Fermi-Dirac statistics, and this extra factor will be called a degeneracy factor, and I'll explain why a little bit later. This is about electrons. Good. So I understand it. Now, when I want to do it for holes, I will require a little bit extra work. By the way, before I get there for the holes, I want to compare it with what I told you before in terms of band electrons. In the band electrons, you see, I did not have spin up and spin down. I didn't consider spin. I just allowed them to sit one at a time, and from here I just calculated this. You remember this table, right? A few slides, a few classes before, and from here let me go back very quickly. So I calculated this quantity, and from here calculated the Fermi statistics, right? That has that 1 over 1 plus EF over minus E minus EF over KT. So that is what I calculated. Now, what is different between a band electron and a localized donor electron? Why did they have different rules for filling up the states? The reason I already alluded to a little bit in a few classes before is the following. Many times you hear this argument, if you have taken a chemistry class, you have heard this argument that there are a certain number of states and every state can be filled by 2 electrons, right? There is this Hund's law and other things where you can fill the electrons, one spin up, one spin down, you can fill them up. That rule is actually, you see, only applies for large solid. And this is a fact that is seldom appreciated. Because you see, when we say that 2 electrons can sit in a given level, what we might have in mind that the 2 levels are 2 electrons can sit very close together. That is impossible. Only in a solid what will happen that the 2 electrons, when they can be in the same level, but physically or spatially as far away as possible, only when they can do that, only then 2 electrons will sit in a one level. The 2 spin electrons cannot sit in one level if they are confined to small space. And the argument people make that if you have, for example, Lx is the size of the solid, then do you remember 2 pi over Lx? These are the Brillouin zone and the first level, the second level, the third level. This is 2 pi over Lx, 4 pi over Lx, and all those. You can calculate the states. But the reason they can stay together is the following. In fact, you could break the solid into two pieces, Lx over 2 and Lx over 2. Again, calculate the states. When people say that two electrons can sit in the same level, they actually mean that they can sit in a separate places within the volume, not in the same place. So you can see the blue upspin one is in a very different place from the red downspin one. And that is why there's no Coulomb interaction, and that's why band electrons can sit. However, in a donor, they are sitting within 2 angstrom of each other, right? Not 5,000 angstrom apart. No hope of two being together. That's why their statistics is different. Now let's talk about holes. Now the holes, what is a hole? Hole is essentially and sort of an empty space in the sea of electrons in the valence band that sort of reflects the motion of the collective electrons, the other electrons here. It's like in a parking lot. Lots of electrons are, lots of cars are there, one empty space, and if I just follow the empty space, then I know where the cars are moving. So that's the hole, you know that already. Now let me make a quick argument before I go to the next slide. I will call state 1, this is a name, I'll call state 1 when hole is present, means I have a hole. When I have a hole, then I have one less electron, right, and one less proton. So that will be n minus 1 charges. When a hole is present, I'll call that state 1. When a hole is absent, meaning how can a hole be absent? Meaning the hole was there, a electron has gone in and filled up the state. In that case, I'll call the state 0. Hole filled means it has been filled by an electron. And then how many charges do I have? I have one extra electron. So I have n electrons, but I have n minus 1 protons. I didn't bring any proton. So I have one extra charge when the hole is filled, right? And I'll call that state 0. Now you remember when I have one band in the conduction band, and when I localized it, I got one level out because it didn't want to donate, and then I got a spin up and spin down. But do you remember the hole bands are a whole lot more complicated? Why is that? Because instead of having one band there, I have two bands. What are those bands called? A heavy hole and a light hole band. And a one a little bit down, what is that called? And split off band, right? It has split off a little bit, so that's what I have. Now when, let's say this donor wants to withdraw his states that it otherwise would have donated, it will withdraw its states from the light hole. It doesn't want to give it to the light hole. It will also withdraw its state from the heavy hole. It doesn't want to give it there. And since they are together, when it withdraws, it will withdraw 4 states because it gave 4 states before to each one of the bands, two states to each band. So now it will withdraw 4 states from there. Now you realize that if the split of band was also closer, if you had 4 bands over there that was sort of on top of each other, it will withdraw how many? It will withdraw 8 states from there, right? So generally in this case it will withdraw 4 states. So now how to fill these 4 states is what I am going to discuss next. Now this is what I mentioned, that it will take away 2 states for each band, and since there are 2 bands, it will take out 4. And let us see how these states are full. Now these 4 states I'll be calling 0, 0, 0, 0 when the state is filled, all filled. 0001 when you have one hole, and 0010 is when you have one hole but in one of the 4 states. This is how it's distributed. And then there are, you can see that there is no 1, 1, because no 2 holes can sit on those levels, localized levels, because the holes have a plus Q charge. It doesn't want another plus Q charge to be there. So no 1, 1, no 1, 1, 1, nothing like that. All those are taken out. Do you see how the 4 in the distribution function will come? Because now you can see that there are these 4 configuration of 1 levels right here. So let's calculate. So previously we had up spin and down spin, just 2. Now I have 4. You see, this is not rocket science. This is very simple. So let's say in the first state, 0, 0, 0, 0, the holes are full because you have brought in an extra electron and the holes are full, and that's why you have a certain number of charge. You can see when you have one hole, then one of the states are missing, the 3 others are full, and so on and so forth. You can easily see how where the other states would be coming from. Now this I have already mentioned, that the 0, 0, 0 level has n electrons because it's full, right? That's how I define 0 level, when it's full, and therefore it has 1 extra charge. And when you go and have 0, 0, 0, 1 level, then you have a hole. In that case, you do not have a charge. And so going from, if you jump from 0, 0, 0, the 4 zeros to any of the other configuration, then your charge has gone down by 1. Why? Because previously it was full. Now it's at least 1 is empty. So your charge has gone down by 1, and your energy correspondingly, it was previously full. Now there is no electron over there. So your energy has also reduced by EA, the acceptor level. So that's why you will have a minus EA. Now this will require you to sit down with your slide, and the reason I wrote it out clearly instead of just speaking is because I'm sure that you are not, probably just by listening will not follow this, but follow this line by line with your printed slide and listen to the lecture one more time. This will become clear, because it's not an easy thing. Most students get out of this course probably never realizing that they really do not understand these things very well. Okay, so I'm done, because I know how to fill the levels. You know, if I wanted to calculate P0000, probability that the state is filled, what do I have to do? I have 0 holes, so Ni is 0, and I have 0 energy, so EI is 0. So I put it over there, I get that. For all the other levels, you can see I have put a -1 for Ni, because going from 0, 0 level to 0, 1 level, I actually reduce electron by 1, and the partition function is for electrons. So I have a -1, you can see. I also have a minus EA, because the energy has gone down by EA, and when I put this in, I'll get an expression. Okay, that is the step 3 and 4 from the previous slide. And if I wanted to calculate the probability that a hole is full, right? In that case, I will again do the standard ratio of probabilities, and do you see a factor of 4 appearing right over there? The factor of 4 comes because the electron is being shared, the state is being shared by light hole and a heavy hole band. If you had now from this, do you see, if you had 3 bands all at the same point, instead of 4, how many would you have? You have 6, right? So in general, depending on how many degenerate levels you have, this number will be changing, and that's why it's called a degeneracy level. Right? Now you can also understand that why there is no 1, 1, 0, 0, because 2 holes will repel each other by Coulomb interaction, and those states are not acceptable. So in general, we are interested in Nd plus. Do you remember what was the Nd plus? In the first slide, I wanted to calculate how many were empty, and that is why in the charge balance equation. So Nd plus means whatever electrons or whatever donors has given away its electron and has become positively charged in the process. And in that case, I should multiply with F00. Whatever number of donors I have, a fraction of them will give away its charge, not everybody, and that's why I multiplied with F00, and therefore I will have that expression. Now you should realize that's where I got the expression on the first page. What about holes? In the holes, the ones that are charged is when a thing is, the hole is acceptor is charged when the acceptor is full, not empty, full, because then it has one extra electron. That's why you see I write Na minus, because it has taken an electron. And therefore, you have to correspondingly multiply it. Remember the meaning of 0, 0 over there. 0, 0 on the top for the donor means it is empty. 0, 0 on the bottom means it's filled. So it's not the same 0, 0 over top and the bottom. You calculate, you get this expression. That's why we had the 4 over there. Okay, so the derivation, the detour we took is sort of ending here. Now, very quickly, I want to point out a few things, that this factor GD is for the degeneracy factor, you know, for different material, for different systems, this value would be different. So the first thing I want to point out that this statement, the distributions are physical. What it means is that when you have a set of particles, the way they distribute themselves in energy, you see, this you cannot do arbitrarily. You cannot say, I have a bunch of particles, I will assume Gaussian distribution. You know, many people do that. Many people, when they don't know anything, the first thing they say, well, I will take Gaussian. Gaussian is when you don't know anything about anything, then you start by Gaussian, because that's at least you can get started. For Fermi-Dirac, when the electron is in a band, only in that case I have Fermi-Dirac statistics. When I talk about photons or I talk about phonons, I have Bose-Einstein distribution. The physics of photons and phonons, they gave rise to Bose-Einstein distribution. When I'm talking about electrons in a localized state, then I have this spatial distribution. Now there are distribution for quarks and there are all sorts of distribution. Every physical particle which follows a certain amount of rules, certain rules will be given by a certain distribution. So distribution is not statistics, it is actually physics, because physics dictates how things can get distributed in energy. Okay. Now I also mentioned the degeneracy factor. But you see, for a theorist, it is easy to calculate in some way this number. Most of the time, experimentalists don't really worry about this, because if you have a new material, you see, in this material we already know how many valence band we have, how many conduction band we have, and this has been calculated over last 50 years, right? People know a lot. Let's say you have a new material. You don't even know where the band is and how they are with respect to this exact position. So in that case, although the GD looks very easy to calculate once you know the band structure correctly, many cases you may not have the band structure known correctly. So experimentalists, what they often do is they say, well, since I do not know, I might do a little fudging. And that's what they do. They say, well, I'm going to still assume that it is a Fermi-Dirac statistics, because I don't know GD, you see. And what they are going to do is write the GD in terms of, GD is a constant, 4, 6, 2, whatever. They will write it as some epsilon divided by KT, you know, that's a constant, and pull it in so that instead of talking about ED, which is the donor level, E sub D, the donor level physically calculated from the hydrogen level, you have a E sub D prime, which is a effective level, because you have hidden the degeneracy in the E sub D prime. Now, once you have set it up, you see all the calculations will come out right, because this is a property of the physical property of the material and the donor. So long you have a silicon and a phosphorus combination, you exactly will have one specific value for E sub D prime. Now, if you go to germanium and you talk about phosphorus, then you will have a slightly different value of ED prime. But in general, you see, in general, the ED value would have been different anyway, because of the different dielectric constant, because of the different effective masses, it would have been different anyway. So why worry about it? We will just set it to a particular value and experimentally determine it. So that's what's called an effective donor level. So this course is full of effective things, right? Effective mass, effective density of state, effective donor level. Because we are engineers, at the end of the day, we'll have to calculate something. Theory is good, but at the end, we need to calculate specific things quickly. Okay, so we are set, and that's where I'm beginning to come to the close again, is now you know the physics of donors, the physics of acceptors, degeneracy level and all. From here, you can calculate this. The one reason you always have to use this full expression for donors and acceptors, but not necessarily for electrons and holes, is because the Fermi level, wherever it is, since the donor level is below the conduction band, most often the donor is in a degenerate level, although donors and acceptors, because it's closer to the mid gap compared to the conduction and valence band. As a result, although you can approximate the first two often, you cannot approximate donors and acceptors as easily. Sometimes you can, but you shouldn't take chances too often because you can be burned. Okay? So to conclude then, we talked about why intrinsic semiconductors do not have too many electrons, right? This I'm emphasizing quite a bit, because there's a very little difference between a semiconductor and insulator. 1 eV band gap is a large band gap for electrons to jump from the valence band to the conduction band. And whether once you have 1 eV or whether you have 5 eV at that time at a room temperature makes very little difference. So therefore, you have to do something about it. That's donors and acceptors. Now, the statistics of these levels are different because these levels are localized, and in the localized levels, electrons repel each other. They cannot have it in a extended band. They don't. That's why the statistics are different. So let me end here. Just also this final point being that the conduction and valence band also behave differently, and that's something I've also tried to explain during the lecture. Okay, so we'll use this information in the next lecture to begin to calculate for various donor dopant levels what exactly are the conduction or number of conduction electron and number of conduction valence band holes I have. Okay, we'll end here. Thanks.